Presentation covers three different parts. The first part is about the changes that we did in our operational IGS processing with the introduction of the new reference frame. Second part, I'm going to report about sub-daily ERP model investigations that we have been carried out. And finally, about our intention to include Galileo into our ESOC routine IGS products. In that context, I'm also going to highlight the importance of having spacecraft metadata in general, for Galileo in particular. So we've done some changes after the switch to the new reference frame and the new Antex file, because we wanted to get our scale closer to the IGS combined scale. So we finally introduced power thrust for GPS and GLONASS satellites that brought us a little bit closer to the mean scale, but not as we have expected it. So then we found that our infrared properties for the GPS 2R and GLONASS satellites, that those values were much too small. So we slightly changed them, basically used the values that are commonly used in IGS. And that brought us very close to the IGS combined scale. I have a plot on the next slide that will show that. Then we had some issues with the Block 2F satellites with a box-wing model, so we decided in April 2016 to turn that model off, as it was doing more harm than good. In the end, that improved the weighted RMS agreement with the IGS to the IGS Final orbit, but it did not improve the scale. So in the end, the decision was made to turn the model on again with slightly changed property values, but it's not still optimal what we do there for the 2F satellites. So this is the famous plot from the ACC side that shows the scale of the individual analysis center orbits versus the IGS scale. Purple is ESA. And you see here the impact of these three different changes that we've done. First, we turned on power thrust, then switched the infrared properties, and then turned on the Block 2F box-wing model with the new values. And now we are more or less in line with what most of the analysis centers do. And this is another plot from the ACC side that shows basically the effect of when we turned off the box-wing model in April 2016. That, as I said, improved slightly the weighted RMS agreement, and then when we turned it on again in this year, the RMS got a little bit up, but it's still slightly better than as the situation was before. In 2016. Then Tim did some testing with instant re-radiation. So he basically took this formula from Fliegel that assumes basically that all the energy that goes into the spacecraft bus, that this is instantaneously re-radiated. So we changed that in the source code of our software and saw some significant changes, but mainly for the GLONASS M spacecraft. There was no change or hardly any change for the GLONASS K satellite. And even more interesting, for the GPS satellites, we did not see anything. That was previous slide was for the cross-track component. This is the radial component. So if you compare those two orbits with and without instant re-radiation, you get some significant effects, but only for GLONASS M. That was a rather surprising result, and the initial reason was unclear. But then we found that for the GLONASS satellites, for the box-wing model, we use the values we use are different for the plus and the minus Z side, whereas for GPS the values we use are completely identical, which is something that is very unlikely given the fact that you have the antenna on the plus Z side, and so and you don't have that on the minus Z side. So there must be a difference. And that indicates that we're still doing something wrong here for GPS. Okay, so this was radiation pressure part. Now we come to the ERP model investigations. Tim has done some investigations already in 2011. he looked into the impact of different subdaily ERP models, among them this IRS model 2010 that we just heard about, and he also tested a model that was developed by John Gibson from Goddard Space Flight Center based on VLBI data. And then John came up with a new model 3 years ago at the workshop, Unified Analysis Center workshop in Pasadena. So he apparently added 4 more years of data to his model, but there was no big change. So in the end, Tim and John agreed to retest this model. And he also tested some other models, two other models from Bonn University, but I will focus here on the effect of this model from John Gibson. You will see that on the next slides. So for his testing, he processed 1 year of data, which is the minimum if one wants to see something in the spectra. For station coordinates, probably even a longer period is needed. He essentially used the IGS, our operational IGS processing setup, however with a limited number of sites, so just 16 sites and rather than 150 sites. The pre-processing was only done once to make sure that all test solutions are based on the same set of data. And that's the most important part now. In 2011, he only had GPS available. Now we have GLONASS and Galileo fully under control. And so the results I'm going to show you on the next slides are for all 3 systems. And you know that all the systems have different characteristics, different orbital repeat cycle and different inclination. And that's very interesting what we are going to see there. So he looked into 2 different metrics. He looked into the orbit overlaps, but into the traditional radial along crosstrack components. And he saw some signals in the crosstrack, but not very clear. And then he converted these differences into Keplerian elements. And there, all of a sudden, a very clear signal in the right ascension node of the ascending node showed up. We will see that on the next slides. He also looked into the ERP differences with respect to the IRS pole, saw some signals in the pole rates and also in the LOD estimates. Saw apparently nothing in the station coordinates, which might be due to the fact that he did not process enough stations. Okay, so this slide shows the orbit overlap residuals for the crosstrack component for the GPS orbits when you use the IRS standard model. You see some power at the 14-day period, but not much, and essentially you see basically 2 peaks, one before and one after 40 days. So let us look into the right ascension of the ascending node. There, a very clear signal shows up for all GPS satellites. It's very clearly, I think. Again, this was based on the IRS model, and next slide will show you the spectra for the Gibson model. And you see the peak is almost gone for all satellites. Now, this was only GPS, and one could say, okay, this is GPS has a draconitic period and 12-hour orbit repeatability. So, is that really coming from the pole? So we now look into the GLONASS orbits. Again, processed first with the IRS model. You see again this pronounced peak at the 14-day period. You also see that there's lots of power around the 8-day period, which is due to the orbit repeat cycle of the GLONASS satellites. And so we're still doing something wrong here, obviously. Again, this is IRS model based, and when we look onto what the Gibson model gives us, you see, can go back again, this peak at the 40-day period is completely gone. Finally, Galileo, the results for the IRS model, again, the peak shows up at the 14-day periods. And if we look on what the Gibson model gives us, this peak is gone. Interesting also is here that the spectra is generally a bit flatter compared to GLONASS. And yeah, so that's this plot contains all the orbits of all 3 satellites or satellite systems again with the IERS model. There you can see it very nicely when Gibson model was turned on, the peak at the 14-day period is gone. As I said, there was also a small improvement, or significant improvement in the LOD estimates. I think I should go quickly through those slides here. So here IERS model is indicated in red and Gibson is in green. Clear improvement here again at the 14-day period. And also see that in the X-pole rate estimates and the Y-pole estimates. Okay, so some conclusions. The results basically confirm what we saw in 2011 with the old Gibson model, but that was just based on GPS. So now we have GLONASS and Galileo, so that should give, I think, some more confidence in the results. We see a clear 40-day period in the right ascension, which is practically gone with the model from Gibson, and that's why Tim proposed a change to the IERS convention to adopt this model, and I think more about this will be discussed next week at the Unified Analysis Center workshop. So yeah, that's it for the ERP modeling. Now we come to our intention to include Galileo into the operational IGS products. I would like to take this opportunity to thank the Galileo project for the very good cooperation that we have with him, since more than 10 years now, basically since the launch of Jofi A. We get now very precise Galileo orbits. We have ambiguity resolution fully under control. Thanks to the metadata that we received for the IOV satellites, and we also have that for FOC, and that will soon be published, as we heard this week a couple of times. Radiation pressure modeling for Galileo is certainly very important because of the very low weight of the satellites and their shape. This is just to show you the impact of a radiation model, the box wing model that we have in our software. When you turn this model on, how the orbit changes. This is for the cross-track component, so you have here really a big impact in the order of up to 25 centimeters, and even more in the radial component of up to 10 centimeters. So it's really necessary to use this model, I think. And finally, a small benchmark test that we have done. It's basically this shows the orbit overlap RMS for all 3 systems. That was a reprocessing over 2016. Blue is GPS, red is GLONASS, and green is Galileo. Left-hand side is ambiguity-free, right-hand side ambiguity-resolved solution. GPS is clearly superior to all other orbit overlaps, but Galileo is getting closer, and it's even better now, or at least our results are at least even better now as what we get for GLONASS. So we get roughly a 3D orbit RMS of 5 centimeters. And by the way, this was achieved with only 11 satellites and only 16 stations. So now we have, meanwhile, 70 satellites, and of course we have much more stations to process. And yeah, that brings me to my conclusions. So knowledge about the satellite impacts the achievable accuracy, obviously. We've seen that minor changes in the box wing model significantly affect the radial and cross-track component of the orbits. What is certainly important for the future is to properly handle the temperature household of the satellites, so to take thermal radiation into account. We have done some sub-daily ERP model investigation, and it turned out that the Gibson model is much better than the standard ERS model. And finally, we intend to hopefully soon include Galileo into our operational IGS products, as we've seen that the overlaps are really excellent, and thanks to the metadata that we received, and we would like to encourage every other GNSS provider to follow and make their metadata available. And yeah, particularly regarding the antenna set offsets, that would probably help enable IGS to contribute to the terrestrial scale. And yeah, that's the end of my talk.